All right, so shall we get started? Is that better? Everybody can hear me with the microphone here. All right, great. So just where we finished last on Friday, if you remember, it was really just introduction, and we got to the point of summarizing these mechanistic classes. As I said, almost all the kind of newer and even the older drugs are in many, many different trials for different types of cancers. So we're approaching it from a mechanistic class rather than this drug is for this cancer. All right. That said, I will give some examples of mainstay cancers to try and illustrate how the drugs are used. But on this slide, really, it's just trying to give you some kind of concept of that these different classes of mechanistic drugs target different levels of that central dogma of biochemistry that we know, the building blocks of DNA, the DNA itself, the RNA that's expressed off that, the proteins, the enzymes, or even the also the cytoskeleton, right? So this is what we're going to go through. And on the next slide, there's just, again, exactly the same summary, but more in words. And as you can see at the bottom here, you know, there's hormones and immunotherapy. When we can't possibly cover all of these, I believe that Dr. Stevens will cover hormones as drugs in his section, and immunotherapy, we got an introduction to it in Pharmacy 748. All right, but what we're going to do is give you some idea of the first 6 of these classifications, and starting with antimetabolites and alkylating agents today. So just to tie it, though, to really the lectures that you got from Dr. Indra, you know, why is it so important to know genetic defects associated with the development of a cancer? What does that let us do? Well, as an example of a success, there is a targeted drug, again, a kinase inhibitor, vemurafenib or Zelboraf, for melanoma patients, and it's only for those patients who have a specific mutation in the BRAF gene. All right, it's like residue 600. And so that can be detected. There's an FDA approved test for that. And then only the people that have that mutation need to be given the drug. Because what you've heard on Friday was just that there's a lot of side effects, especially to the fast growing cells of your body, because we're trying to kill our own cancerous cells in the presence of our own healthy normal cells. And if we didn't have to give somebody a drug, a lot of cancer chemotherapy, there's a lot of toxicity because we give the patient the drug a little bit experimentally. Oh, let's see if this will work for them. Let's see if this will work for them. With cancer drugs, that's really dangerous because they are so toxic. They're designed to kill cells. So this is really, you know, what we could envision for the future, the ideal. What are the challenges? Now that we know we can do it, why can't this just happen? Well, you know, we don't have comprehensive analysis of all the cancer genomes. There's enormous diversity in the genetic abnormalities found within cancers, even of a single type. And when you think about it, this makes sense. All of us are exposed to different kind of environmental assaults and different stresses and different things that affect our DNA every day. And we're all individuals. So the progression of cancer as we age, or potential for cancer as we age, is different for each of us, all right? It's difficult to acquire the biological samples needed for genomic studies, especially for rare tumors, right? Not all of these, we can't just walk out and find a population of people with that cancer who are willing to give us a biopsy. That's pretty painful to obtain potentially. So especially for those cancers that aren't treated by surgery, so there's no opportunity during surgical resection to get a sample of that tissue and to genotype it, all right? And then more than that is to get it contributed to these very broad big data studies, which could tell us something ultimately about the trend for that cancer. And then, you know, further from that, cell lines and animal models, especially of rare cancer subtypes, may be non-existent or underrepresented. There's no models for many current genetic mutations in human cancer. And we tend to always work with the same models. It took Dr. Indra and his laboratory many years to develop a handful of models. And then some of those models are prioritized around the world for research. But so there's very, very few research tools to generate the knowledge. All right, so that kind of is a segue then into why we're going to talk about these old mainstay drugs that are used very effectively in combination. And today, the focus is really anti-metabolites and alkylating agents. So to begin with, what I chose was to just couch this in the framework of colorectal cancer. This is one of the really most common, unfortunately, cancers in the Western world. In the US, new cases, 153,000 just in 2023. All right, deaths was about a third of those. And the 5-year survival rate is 65%. So with this, there's actually not been much change. Every year I update this number. I go to the websites down below, cancer.gov and the Colon Cancer Foundation, and I update these numbers. And for this cancer, it's really kind of stayed the same. There's not much change. I mean, to within a 0.5% of the numbers are staying the same, right? And that's because this is a very difficult cancer sometimes to detect. If it is caught early, stage 1 and stage 2, the best course of action there is usually surgical resection. So if there's a site of cancer, that portion of the colon can very effectively be cut out. And then there would also be adjuvant chemotherapy to try and mop up those last cancer cells as well. For stage 3, where there's already lymph node involvement, so some metastasis, certainly surgical resection of the primary tumor, perhaps the regional lymph nodes taken out as well, and that adjuvant therapy. And these are the kinds of therapies for colorectal cancer: 5-fluorouracil and leucovorin, all right, in combination called FULV. Capecitabine, Xeloda, all right? And so what do you recognize about the name 5-fluorouracil? What does it have in it? It has uracil, right? It's very close to uracil, which is one of our own endogenous nucleobases. So this is an anti-metabolite because it's designed to be just like our own metabolites that are the building blocks of DNA, but it's got that 5-fluoro group on it, which is going to cause major issues for enzymes and for enzymes in the assembly of DNA and in activation of building blocks. All right, so leucovorin 2 is actually a folic acid analog, and we'll learn about those today. The only other thing I want to point out here is capecitabine. When you see the name being some variation of that, an INE and kind of 2 syllables there, it's probably also an antimetabolite. All right, these are the purine and pyrimidine analogs. So 5-fluorouracil is a pyrimidine analog. All right, and we'll see a little bit more about that. So in another combination, 5-fluorouracil, leucovorin, and oxaliplatin. So oxaliplatin, one of the platinum drugs, this is an alkylating agent. It's called alkylating, although it's kind of platinating more than alkylating. But we're going to talk about those today as well. So a lot of the drugs here are antimetabolites and alkylating agents for colorectal cancer. These were drugs that were discovered a long time ago to be efficacious, and they're still used very effectively in combination. Irinotecan is a topoisomerase inhibitor. Tecans, the name tecan is almost universally applied to topoisomerase 1 inhibitors. And so you can see these combinations, especially for stage 4, where there's probably not a good prognosis, but chemotherapy can go a long way for palliative care, for reducing the tumor, for extending life. So FOLFOX, FOLFIRI, we'll see these on the next slide. These kinds of names, you could think colorectal cancer. All right. I'm not actually so concerned about the combinations and you recognizing the combinations as the individual drugs. And I won't be asking you in the exam what drugs are in this combination. I think we're just not there yet. All right. And what I want to highlight under the stage 4 drugs is really, yes, the first few are largely what I've been saying, mainly alkylating and antimetabolites, or the topoisomerase 1 inhibitor, irinotecan. So whenever you see irinotecan, or whenever you think colorectal cancer, it would be good to think irinotecan. All right, irinotecan, colon cancer, that's just a good pairing. Same with 5-fluorouracil, colon cancer. That's always a good kind of pair to make in your mind. One of the very promising things is that there are some kinase inhibitors. Do you recognize the name ENEB, regorafenib, NIB at the end? That's a kinase inhibitor. And then adagrasib. This is a very, very new type of kinase inhibitor that just until recently, researchers thought it was impossible to inhibit KRAS, all right, this GTPase protein. And now, in fact, they've shown that it's possible, and this is an approved drug. So again, another kinase inhibitor. So as I mentioned, some of the really still common, very common, if you go to the websites for colorectal cancer treatment, these are what you'll see: Capox, Xeliri, FOLFIRI, FOLFOX. And so just to keep in mind then, capecitabine, oxaliplatin, irinotecan, these are the drugs of colorectal cancer, and they're antimetabolites and alkylating agents. So what is an antimetabolite? I kind of introduced you there by saying, well, uracil. Uracil is a metabolite in our bodies. It's one of our endogenous metabolites. So an antimetabolite is something that goes against those metabolites. They prevent the biosynthesis or use of normal cellular metabolites. They're structural analogs of the metabolite that's being antagonized, or they're a cofactor of their enzymes or an end product. And so what they really do is to interfere with the production of nucleic acids. And there's two ways that they do that. They can compete for binding sites on the enzymes that assemble the building blocks. Remember, once you've got a nuclear base like uracil, you need to put a sugar on that, or the body needs to put a ribose or deoxyribose on that to make a nucleoside, and then that's phosphorylated to make a nucleotide. And the enzymes that do that could be inhibited by these antimetabolites, all right? But the other thing is that the antimetabolite, well, maybe it just gets activated by the enzymes that phosphorylate and ribosylate, and then that antimetabolite can get incorporated into the DNA as if it were just a regular DNTP nucleotide, right? Deoxynucleotide. So they can either compete for binding sites on the enzymes, and or they can be incorporated into the DNA itself. And maybe they get all the way there, and then suddenly when the DNA is supposed to make this beautiful symmetrical helix, suddenly there's a nuclear base with an awkward arm sticking out, and that stretches the helix or otherwise disrupts it, and that would flag DNA repair enzymes would have to come in and see, can those repair enzymes repair that so that the helix sits properly, or is that going to be a cause of cell death? All right, so incorporation into nucleic acids of unusual structures is normally a big flag for the cell then undergoes apoptosis, all right, because it can't have that DNA not be in the perfect helix. It means that there's something wrong, all right? So 3 categories of antimetabolites: folic acid derivatives, or vitamin B9 is folic acid, all right? These are actually enzyme cofactors. And so these were some of the earliest designed drugs in the 1940s. People realized that you could actually use inhibitors of the enzymes that produce folic acid as a cofactor for the cells to grow and divide. And we'll see exactly what steps that's at. Pyrimidine analogs, all right, so these are the pyrimidine antimetabolites. They look like pyrimidine bases. 5-fluorouracil is in there, and we'll see some other structures of these, but the 3 drugs highlighted in blue are the only ones we're going to talk more about. There's also purine analogs. These have more the fused ring system of the purines: 6-mercaptopurine, thioguanine, pentostatin. You can see some of these, mercapto and thio, means that they've got sulfur in them. Certainly our endogenous metabolites don't have sulfur. All right, so if you need to review purine and pyrimidine bases, here's a quick cheat sheet, but certainly go and read more about it if you need to. Here is the classic purine ring structure, and below the pyrimidine ring structure, and then the 4 purine bases: adenine, guanine, hyperxanthine, xanthine. And you can see how adenine has this NH2 up here, whereas guanine has an oxygen at that position. It has an NH2 in the kind of southwest corner. And then the pyrimidine bases, just the single ring, cytosine versus thymine. And you can see they really differ in the nitrogen and oxygen groups, substituents that they have, the pendant nitrogens and oxygens, and then also the nitrogens in the ring can be variously basic or nucleophilic, and that changes their activity, as we'll see for alkylating agents. So really something to just keep in mind, have firmly in the back of your mind the difference between purine and pyrimidine. All right. So folic acid derivatives first. Hopefully on this slide, really, we can't learn all the drugs in each class, but I hope that you can see here is the endogenous metabolite folic acid, otherwise known as vitamin B9 or vitamin M or pteryl glutamic acid or folacin. In the structure, hopefully you can see is there's a fused planar ring on this kind of west side, the left, as you're looking at it. And then there's a bit of a linker with a nitrogen in it. And then there's another benzene very so planar aromatic ring, and then there's some kind of side chain. So fused ring system, linker, another planar aromatic, diffuse electron density there, and then a side chain. And if you look at the drugs that are used in the clinic, leucovorin or folinic acid, again, inherently, it's got two fused rings, a linker, a benzene ring, and a side chain. Methotrexate, two fused rings, a linker, a benzene ring, and a side chain. Obviously, some variations between them that change a little bit the way they work, but inherently, they all look the same as the endogenous metabolite. So they're an anti-metabolite, and they all operate quite similarly. But you can imagine they have different solubility and drug delivery characteristics than ADME characteristics. So these are, as we said, starting in the 1940s, and really methotrexate is the one that you might be most familiar with, because that also we learned about in as a drug for rheumatoid arthritis. So what do these do? Well, they are cofactors, as we said, and they're cofactors for the enzyme thymidylate synthetase. Thymidylate synthetase changes the uracil in uridine monophosphate by adding a carbon so that it becomes thymidine. So hopefully you can see this red carbon, this red methyl group here on the thymine base in thymidine monophosphate. That is the addition of carbon onto uracil. All right, where does that carbon come from? All right, the carbon comes from the cofactor. The carbon comes from, it's really this methylene group in the cofactor cycle here. So N5N10 methylene tetrahydrofolate is the cofactor for thymidylate synthetase. And when it's donated that carbon, the cofactor then reverts back to just dihydrofolate. All right. And then dihydrofolate can get reduced again and a carbon added so that it can donate that carbon again in the reaction catalyzed by thymidylate synthetase. All right. So dihydrofolate that's left over after the thymidylate synthetase action, this needs to be recycled, and it is reduced by dihydrofolate reductase. So dihydrofolate reductase reduces dihydrofolate to tetrahydrofolate, right? Reducing means normally adding hydrogen. So dihydrofolate to tetrahydrofolate, it's added two hydrogens, right? So it's reduced with the aid of NADPH, which you don't have to worry too much about. But what we do, so this would be normal cycling for folic acid, the endogenous metabolite in our body. What we do when we add a drug like methotrexate or pralatrexate is we inhibit dihydrofolate reductase. So methotrexate and pralatrexate inhibit dihydrofolate reductase. They don't inhibit directly, like they don't bind to thymidylate synthetase. They bind and directly inhibit dihydrofolate reductase. All right. So once we've added methotrexate or pralatrexate, we don't get any tetrahydrofolate because that dihydrofolate reductase enzyme doesn't work now. All right. It is inhibited. So when we don't get any tetrahydrofolate, we don't get any methylene tetrahydrofolate. If we don't have methylene tetrahydrofolate, then we don't get that extra carbon to add to the uridine. So we then don't get the product of thymidylate synthetase. All right. So does that make sense? That's just kind of the story of what happens when you inhibit a cofactor. And the next slide you can completely ignore if you would rather, but what I found when I left it out last year is that some people really asked after it. So it's just in there. And it's just a little bit of more detail of what is going on in this cofactor cycle. And I should say, sorry, that when one of the issues is when you add these drugs or even a different cancer agent that inhibits thymidylate synthetase, some people have real dose-limiting toxicity from this block of dihydrofolate reductase, and their dose needs to be balanced. So leucovorin actually can be added as a rescue agent. It doesn't need to be reduced by dihydrofolate reductase. It already is already reduced, and it can carry on in this cycle and end up being the donor for thymidylate synthetase. So it rescues the action of thymidylate synthetase if needed. So it's known as a rescue agent when people are having severe side effects and need immediate assistance. They can give leucovorin as a rescue agent because it's already in the tetrahydrofolate stage of reduction, right? It doesn't need to be acted on by dihydrofolate reductase, which has been inhibited by methotrexate. So this is kind of like an antidote, kind of like an anti-venom if you got bitten by a snake. The venom's already in you, the methotrexate, pralatrexate's already there, and now we need to undo the effect that's happening because it's too toxic. So we're just going to give a rescue agent, and in this case, that rescue agent is leucovorin. All right. So this is the next slide I was talking about, just to show you the structures. Dihydrofolic acid. What happens is this double bond in the north here is reduced by adding 2 hydrogens across it. So now we get tetrahydrofolic acid. This is the enzyme catalyzed by dihydrofolate reductase. That tetrahydrofolic acid actually accepts a carbon from serine. I should have asked you, do you recognize what this amino acid is? But I just gave it to you. All right. Serine is an amino acid with a side chain CH2OH. And so that whole side chain is put onto the folic acid, and the carbon, the CH2 from serine, becomes the CH2 that we've been calling the methylene carbon on the tetrahydrofolic acid. All right. And then thymidylate synthetase takes that carbon and adds it to uracil in the previous slide to get thymine. And this, when it loses the carbon, goes back to dihydrofolic acid. All right, so these are just showing the chemical structures for the catalytic cycle on the previous slide. But what's missing is that this carbon really goes here, right? That's the carbon. So just in case you're interested, you don't need to worry about that slide if you don't want to. So leucovorin, folinic acid, the great thing about these drugs is that they are oral, so they can be given orally. That's a really big plus for in dealing with a person who has cancer. Indications, then, it's used as rescue therapy when there's toxicity to pralatrexate or methotrexate. So it's the antidote for those. It also enhances the cytotoxic effect of 5-fluorouracil. All right, so it actually enhances the effect. And if you think about it, that kind of makes sense because it is feeding that catalytic cycle of the cofactor, making sure there's plenty of cofactor for really thymidylate synthetase to take 5-fluorouracil and try and convert it to thymidine. And what you want is you want cancer cells to do that as much as possible, because what happens is that thymidylate synthetase then gets blocked up by 5-fluorouracil, and it can't let go because fluorine is not a good leaving group. So if you induce that cycle to happen, you kind of get everything, you get thymidylate synthetase stuck up, and the cancer cell will die because it can't make the building blocks for DNA. It can't grow and divide rapidly. All right. So this rescue agent actually enhances the cytotoxic effect of 5-fluorouracil. And that is very important to think about if somebody's having side effects from methotrexate or pralatrexate. Hopefully they're not taking 5-fluorouracil as well, because you certainly have to be very careful about that. All right. So again, we've discussed the pharmacology. It doesn't require reduction by dihydrofolate reductase. And so it enhances the biosynthesis of pyrimidines. It overcomes that blockade of tetrahydrofolic acid production in normal cells. So this also, remember we said the toxicity that's dose limiting often is actually in the normal cells of our gut and liver and our other organs with very high cell turnover. So this rescue agent will help those systems recover if that's the cause of the dose limiting cytotoxicity. Leucovorin actually also has another action, which is to block the transport of methotrexate into cells. So if somebody's experiencing toxicity because of too high a dose of methotrexate for them, this is good because this rescue agent also kind of blocks the uptake of the excess methotrexate, and it stimulates its efflux. All right. And then, as we've mentioned, it enhances the toxicity of the 5-fluorouracil. And so really the one that I want you to just remember is that because it doesn't require reduction, it really overcomes that blockade. All right. And the side effect and toxicity, really just remember that it enhances the cytotoxic effects of 5-fluorouracil. There is an allergic sensitization that can be severe, but the cytotoxic effect one is the one that I want you to remember for now. And then really methotrexate, just as probably the drug you're most familiar with and may have seen in practice, this can be given in many different forms: IV, oral, intramuscular, intrathecal. So this is a very versatile drug. As we've really emphasized, it inhibits dihydrofolate reductase. It's essentially irreversible. And so because of that, it really blocks the synthesis of thymidylate, all right, of those building blocks. And it actually can block purines as well, because other enzymes that make DNA building blocks also require folic acid cofactors. So what does this mean? Really, if it's blocking that synthesis of building blocks, it affects the S phase of the cell cycle, right? The synthesis phase of the cell cycle. It's most effective in the logarithmic growth phase. So it's just a little bit better at targeting those fast growing cells, which is ideal. So that was the folic acid analogs. Just to go on to the pyrimidine analogs, thymidine monophosphate and cytidine monophosphate on the left-hand side are the endogenous metabolites, just for your reference. So you can see how similar the structures are. So those are our endogenous metabolites. And then we've spoken a lot about 5-fluorouracil. You can see how simple it is. It just has a fluorine, where uracil would have a what? A hydrogen. All right, so uracil has a hydrogen, 5-fluorouracil just has a fluoro there. And if you remember from some foundations of drug action, bioisosteres or isosteres, fluorine is quite similar in size to hydrogen and is often used by medicinal chemists as a replacement for a hydrogen, because it's not very much bigger. the issue is it doesn't like to leave, right? It's extremely electronegative, and it's not going to leave like a hydrogen would in an enzyme catalyzed reaction. So that will be important down the road. And some other commonly used ones, for example, in combination, when I looked more recently, this seems to be one of the common combinations, trifluoridine and tipiracil or Lonsurf. And what I want you to take away from this slide really is just the recognition that these are pyrimidine antimetabolites. There's also cytarabine, gemcitabine, capecitabine, and these you will see very commonly in the drug combinations, as we've already seen for colorectal cancer, and certainly for the other cancers that we talk about. So I also just think, yeah, capecitabine is probably one of the newer, most versatile drugs in many combinations at the moment. All right. So 5-fluorouracil, this is the only one that we're going to talk about. Just a little bit more about that. Again, 1950s and rational drug design, Heidelberger observed that certain tumors use uracil more than orotic acid. All right. So orotic acid is just the nucleic acid pyrimidine precursor in normal tissue. So normal tissue likes to use orotic acid. Tumors like to use uracil. That's good because there's some selectivity there then, that maybe we can target tumor cells that are using uracil, and normal cells that use orotic acid more will be not as affected, more protected. All right. The administration of this is IV. You may also know there's a topical form for actinic keratoses. That's what I've got on my nose. That's why my nose is red. I could put 5-fluorouracil on that, and it would be very effective. So it does come in different forms, but for cancers, it's normally given IV in combinations. So the pharmacology, as we've already mentioned, it inhibits thymidylate synthetase, that enzyme that puts a methyl group on uracil so that it becomes thymidine. And because of that, it's incorporated into DNA and RNA. So instead of UTP being incorporated, you've got this FUTP, fluoro-uridine triphosphate. All right. The rate of catabolism of the 5-fluorouracil is determined by this enzyme dihydropyrimidine dehydrogenase. And it's possible that if people have very active dihydropyrimidine dehydrogenase, that can be inhibited by a different uracil, this 5-ethinyl, to raise the 5-fluorouracil therapeutic index 2 to 4-fold. All right. Some patients will naturally have a very low expression of dihydropyrimidine dehydrogenase. And this can be very dangerous because the doctor will start off by prescribing a certain dose of 5-fluorouracil, and it turns out that to that person's body, it's at least 4 times the dose that the doctor thinks they've given them. All right. So there's actually a check for this enzyme, dihydropyrimidine dehydrogenase. You can get typed for whether you produce DPD, but it's quite expensive. And so hopefully that's something that will change in the future. Side effects and toxicity of 5-fluorouracil. The two that I really would like you to remember is dose-limiting myelosuppression. Myelosuppression specifically is low granulocytes and low thrombocytes. All right, so the thrombocytes for blood clotting are low, granulocytes in the immune system low. So, why does that happen? Remember what we said, that some of the fast-growing cells in our body that are constantly growing and dividing are in our bone marrow. And so those will be affected by this drug. and cause myelosuppression. All right. And then the other important side effect that I think is very much associated with this drug is cardiotoxicity. So there is this effect on the heart muscle. Again, the heart is very metabolically active, and so cardiomyocytes are very have a higher turnover, and so they can be cardiotoxicity. Otherwise, the other side effects, you don't have to. I don't want you to just memorize them for this drug and then memorize a different set for a different drug. I'd like you to know those two main ones, but if you think about it, the others you could guess at: GI toxicity, stomatitis, so like sores in the mouth because those cells have been affected, alopecia, hair falling out, right? The same keratin issue showing as partial loss of nails, hyperpigmentation, and vein toxicity. This vein toxicity is part of the just blood vessel walls that are normally quite high turnover, especially in capillaries. Those will be affected. So skin irritation and some neurotoxicities. All right. So metabolic activation of 5-fluorouracil. Does 5-fluorouracil require metabolic activation? Yes, it does, because even uracil in our bodies, just that nuclear base, that pyrimidine nuclear base, you can think of it as always requiring activation. They need to be ribosylated or deoxyribosylated, and then they need to be phosphorylated before they can be used as the building blocks for RNA and DNA. So if you see the question, does 5-fluorouracil require activation? Yes, it does. All right. So here, adding the sugar 5-fluorouracil riboside, and then there's this enzyme uridine kinase. Kinase is a phosphorylating enzyme, right? So that puts the phosphate on, and you get this 5-fluorodeoxyuridylic acid. And this is the concept of some of those other pyrimidine drugs on the slide, on the summary slide that we showed you. Some of them already have the sugar and the phosphate, so they wouldn't need metabolic activation, right? They've already got those there. So they could just be straight away incorporated into DNA. But 5-fluorouracil needs to be acted on by these different enzymes, and phosphoribosyl transferase is present in higher amounts in some tumors. That's another enzyme that would phosphorylate this deoxyriboside. So the riboside on the left and the deoxyriboside, they both need to be phosphorylated by these two different enzymes. And so can you think if just conceptually, if a cancer cell if it wanted to be more resistant to 5-fluorouracil, what could it do? Yep. Exactly, yeah. It could just start to reduce the expression of these enzymes. That's a double-edged sword, right? Because it needs those enzymes to make building blocks for DNA so that it can grow and divide quickly. So there's a balance, but that is just to start helping you think about the kind of the way in which resistance works. Is a cancer cell could upregulate or downregulate an enzyme, and it can do that because normally there's multiple different pathways to the same thing. So it could be that it can use another enzyme, but the specific enzyme that phosphorylates 5-fluorouracil is downregulated. All right. So purine analogs, again, all we've got here is really just for you to see the structures and recognize them as purines. So on the left, the endogenous guanosine monophosphate, adenosine monophosphate. You can see the fused rings of the purine at the top. then again with the ribose or deoxyribose sugar and the phosphate group, all right? So guanosine monophosphate, what looks like that, mercaptopurine, you could see the sulfur instead of the oxygen at the top here. And then thioguanine, very similar. It's got a nitrogen here. It's more like guanine, but guanine would have an oxygen here where this has got an SH. All right. So thioguanine, and then adenosine analogs, cladribine, fludarabine, pentostatin. You can see these already, in some cases, have a sugar and a phosphate group. So would fludarabine phosphate need to be metabolically activated? No. All right, it's already got, it doesn't need enzymes to activate it by putting these groups on. It's already got those sugar and phosphate. So it's already a like nucleotide, a nucleotide that's ready to be incorporated into DNA. All right. And let's just see. All right, so we've got 5 minutes. Does anybody have questions specifically about those anti-metabolites? And anybody on Zoom? I don't see anything in the meeting chat. All right, that's great. I think, you know, hopefully for these, that should be quite clear. Again, a lot of it is more about the recognition and then just knowing maybe more about 5-fluorouracil than anything else. So, and here's a question from Abigail: is fluorouracil IV more effective? You know, so the question is fluorouracil IV more effective than topical fluorouracil for basal cell carcinoma? I am not the right person to ask that. I think that IV would be more effective because of the dose that it can be given in. There is a 5% topical solution, which is quite high and seems to be very effective, but I'm not sure that it would get down as effectively to the basal cell there. I think about 20% of it gets absorbed. You might put out. Oh, yeah. Thank you. So maybe the people in Portland can tell me how much of that did you hear, because the microphone died. Was it maybe just that last bit? Yeah. Just the last bit. All right, all right. So as I was saying, really, I'm probably not the right person. I do know that the topical, for the topical cream, about 20% of it can possibly get absorbed systemically, but I think it's very much more localized and it's more effective for the upper layers of skin. So yeah, I would really go by what the doctor says for IV versus topical for basal cell carcinoma. All right, and I can look it up as well and maybe give you more information on that. Yeah, all right. So alkylating agents, if we just move on, in 2 minutes, we can just get through the slide again, review that what is alkylation? Really, it's replacing a hydrogen on an atom by putting an alkyl group. So taking the hydrogen away and putting an alkyl group. And that is a substitution reaction, right? Alkyl group instead of hydrogen. And normally what it requires is a nucleophilic atom, in this case of DNA or protein, and that would displace the leaving group from the alkylating agent. So we need a nucleophile, we need hydrogen, and then the alkylating agent, here represented as alkyl Y, would really be attacked by the nucleophile, and you would end up with the alkyl group on the nucleophile, and then hydrogen leaving as a proton and combining with the Y group of the alkylating agent. All right. So what that means is we really want to think about the nucleophilic sites of the DNA bases. Thymine, adenine, cytosine, guanine, they have different nucleophilicity because they have oxygen and nitrogen in different positions around the ring. So the color of the shading indicates the intensity of the nucleophilicity. Thymine, okay, oxygen, this nitrogen and this oxygen, they are somewhat nucleophilic, but in adenine, N3 is much more nucleophilic. So N3 of adenine would be the most nucleophilic site. And then same thing with the cytosine and guanine pair. Cytosine, the nitrogens and oxygens are not that nucleophilic. In guanine, it's N7. The most nucleophilic site is really N7. The oxygen at 6 is also pretty nucleophilic, and that's an advantage because it's a little bit, it's pendant, it's a little bit away from the ring, so it might be more accessible. But in guanine, that's what we're going to focus on. Often, if you've got a question, where is the site of alkylation, just think N7 of guanine. O6 is also on the same face, and so often there's just this attack here. The nucleophile on this face would be what interacts with a drug, for example, all right, an alkylating agent. All right, so let's stop there just for a 10-minute break, and then we'll carry on.
Oh, yeah. Really yeah.
All right, should we carry on? Just before we carry on with this, I just want to follow up with the question that was very good. Thinking about the leucovorin as a rescue agent versus leucovorin enhancing the toxicity of 5-FU. All right. I think the easiest way to think of that is think about it for two different as if it's for two different applications, right? Leucovorin as a rescue agent for toxicity from methotrexate and pralatrexate versus leucovorin added to 5-fluorouracil treatment in a different patient to enhance the toxicity by kind of keeping that thymidylate synthetase reacting with 5-fluorouracil to tie it up irreversibly. All right, so it's not all necessarily happening at once. It's that it would be a rescue agent when somebody's being treated with methotrexate, pralatrexate. That's when it can be a rescue agent. With 5-fluorouracil, it's actually given intentionally to enhance that toxicity often. So there's no dose, it's not like that patient's reached dose-limiting toxicity there. All right. All right, great. So continuing on then with alkylating agents, on the previous slide, we said that very commonly the alkylation site is N7 of guanine. All right, that's going to be the most common one to think about with the drugs that we talk about. And just to remember, reviewing normal DNA base pairing, G and C together and A and T together, in each case a purine and a pyrimidine, to give that correct spacing across the helix. All right. So as I said before, we just really want that regular helix, and anything that adds to it and disrupts it will immediately flag the cell as something's wrong, because the integrity of DNA is really the number one concern of those DNA repair enzymes. So what happens? The consequence of the alkylating agent adding the alkyl chain onto a nucleophile of the nucleobase, alkylation of DNA happens either at N7 or O6 of guanine, as I mentioned, at that face of guanine that's actually exposed in the DNA base stacking. And if available, that you can also have like a second cyclization or second side chain that forms a covalent bond with another nucleophile, another nucleophilic atom on another nucleobase. So some of the agents we're going to see actually have two reactive alkylating groups, and they can first alkylate one strand, and then they can go and alkylate across the DNA and alkylate a different base and actually do inter-strand or intra-strand alkylations. All right. So it doesn't necessarily just happen once. So the result of this, the consequence is DNA base mispairing. If the DNA is left as is and is not flagged for repair, this leads to a mutation that could cause misreading of DNA. So base mispairing and mutation, DNA strand cross-linking, and DNA strand cleavage. Sometimes the alkylating agent goes, it kind of induces a reaction where it ends up in a leaving group coming off the DNA that causes a strand break. All right. So these are cell cycle phase non-specific. The DNA damage happens during all phases of that cell cycle. And remember, that's a little different than some of the anti-metabolites we talked about. They were S phase specific during the DNA synthesis. All right. That's when they are, that's when the anti-metabolites were more effective. But these alkylating agents are not cell cycle phase specific. What happens when they alkylate DNA is they activate cellular responses like cell cycle arrest, DNA repair, and if the DNA can't be repaired, then the cell undergoes apoptosis or programmed cell death. So that's always kind of the sequence of events with cell cycle arrest. Then DNA repair is attempted. If that's not successful, apoptosis is the pathway that happens, and the cell is taken out of circulation. So these agents that are non-cell cycle phase specific, they're more cytotoxic to rapidly proliferating cells, right? So rapidly proliferating cells, it doesn't matter what phase of the cell cycle, the cell division cycle they're in, they're going to be susceptible to these agents. Our normal cells, mostly our somatic cells, are just in the G0 resting phase. So they're not undergoing that cell division cycle. So they're not as susceptible to these agents. But obviously our liver, our GI tract, our epithelia in general, our hair, those are rapidly proliferating and they will be affected. And for the alkylating agents, cytotoxicity just correlates very well with the level of interstrand cross-linking. So an agent with 2 alkylating arms will be more effective than the same dose of an agent with 1 alkylating arm, because that bifunctional alkylating agent can cross-link that many more DNA bases. So these again are some of the really, really early drugs. The nitrogen mustards were stumbled on during the World Wars, really in World War I. These were, the sulfur mustards were discovered as blistering agents, and the systemic effect of those drugs was found in soldiers upon autopsy, and they realized that this systemic effect could be useful, especially in blood cancers. So they were, when I think of these nitrogen mustards, I always think of blood cancers, because they're used to treat a lot of leukemias and lymphomas, as well as in combination for other cancers. What you can see here is the classic structure of these nitrogen mustards. There's a nitrogen in the middle that has 2 alkyl groups with the chlorines on. So chloroethyl, the alkyl is the CH2CH2, and then it's got a good leaving group, the chloro, all right? So in this case, it's a bifunctional one because it's got 2 chloroethyl groups and a methyl group from chloroethylamine. So this drug is by far the most reactive. It's highly reactive with water, and it's very difficult to control it. It is essentially a blistering agent. So there was a lot of medicinal chemistry that was done around these to stabilize them more. And chlorambucil, here you can see it's very similar. There's a nitrogen with these two chloroethyl groups in red, but instead of the methyl group of mechloroethamine, there's a whole benzene ring with a side chain. And what that benzene ring does is it delocalizes the electron density from the nitrogen into the benzene ring. So the nitrogen's not as reactive, and that means that it's a little more stable and kind of less reactive in the body, and makes a more manageable drug. There's many different variations on the theme, but I hope you can see here. So bendamustine, ifosfamide, uracil mustard, cyclophosphamide. I hope you can see in all of these, they have the two chloroethyl alkylating chains in red. But what's attached to that could vary. Uracil mustard, then, how would you classify uracil mustard? Is it just an alkylating agent? What else could it be? It's an antimetabolite as well, right? Yes, yeah. It's actually, when you think about the mechanism, it could be that it acts as an antimetabolite as well as an alkylating agent. So these compounds all have varying reactivity, and that's what we're going to talk about now. So mechloroethamine versus chlorambucil. As I said, this was one of the original nitrogen mustards, Mustagen, developed really starting to be developed in between the world wars, and it's given intravenously. It's because it's very reactive. It has to be given as soon as it's formulated. So it's made up and then it's given IV straight away. All right, within just a few minutes. So that's fine, but it's a very powerful blistering agent, nausea and vomiting, myelosuppression, infertility. What do those all, that first row of nausea, vomiting, myelosuppression, infertility, right? Those are all just those hallmarks of attacking rapidly proliferating cells. It also leads to secondary malignancies. It's so reactive, it can cause a lot of damage, especially if it if it undergoes extravasation, right? If it goes through the vein, out of the vein into the surrounding tissue, that's kind of a very urgent situation where they have to quench it with some kind of thiosulfate type solution. All right, so it is itself carcinogenic, mutagenic, teratogenic, and as it says here, extravasation is countered with sodium thiosulfate to protect their tissues. All right. All of these side effects and toxicity also apply to leukeran or chlorambucil. But as I mentioned, this is stabilized because the lone pair of electrons on the nitrogen, remember nitrogen is trivalent, it has 3 bonds, but it also still has a lone pair of electrons. So that lone pair of electrons in chlorambucil is delocalized into the benzene ring. So really joins that pi cloud in the benzene ring, and then that stabilizes it. It's just a little less reactive. And what that means is it can actually be given orally, right? It's stable enough to be formulated as an oral drug. The pharmacology of it, though, is that it's rapidly metabolized to phenylacetic acid mustard, which is also active. And what that means is the body just oxidizes this chain here down so that with the loss of carbon dioxide, that you've got a much shorter chain just phenylacetic acid, 2 carbons, right? So you would just have the acid over here instead of all the way out there. Quickly gets rid of 2 carbons through loss of carbon dioxide. All right, so the main take-home message here is this compound is less reactive than chlorothamine because of that nitrogen electron delocalization. I think that medicinal chemists thought that there would be a lot more scope to work with these compounds, but in general, they're pretty unpredictable. And even though there were hundreds and hundreds of analogs, there wasn't really the success seen with them. I think because their target is so universal. So those are 2 that vary in reactivity. Here is cyclophosphamide, and cyclophosphamide is so unreactive that it actually requires metabolic activation. All right, so we've gone from extremely reactive that it's almost hard to control to so unreactive that it must be metabolically activated. And so here we have cyclophosphamide in the middle row here. The hepatic cytochrome P450s are what oxidize that into this carbanolamine. As you can see here, putting this hydroxyl means there's an alcohol and an amine. We call that a carbanolamine. So once that's oxidized, then that ring of the cyclophosphamide can break, and we get this aminoaldehyde here. And it's really that's the activated product that can go down two different pathways. All right. So cyclophosphamide by itself without hepatic cytochrome P450 activation doesn't do very much. This aminoaldehyde, it can actually be detoxified by aldehyde oxidase, where it's broken down to these inactive metabolites. Essentially, you can see this, it's just cyclized it back to the inactive cyclophosphamide, basically. So aldehyde oxidase kind of is like a detoxifying agent that reverses the metabolic activation of the hepatic cytochrome P450s. The business end is what happens non-enzymatically. So the aminoaldehyde can non-enzymatically spontaneously be converted to this phosphoramustid and acrolein. All right, so, and it's the phosphoramustid here that is, so you can see phosphoramustid is just the aminoaldehyde with the side chain really removed, so all the alkyl groups there gone, and a hydroxy replacing it. So this is really the active metabolite, phosphoramustid. This is the toxic metabolite that attacks the cancer cells. All right, it's phosphoramustid is the compound where the chloroethyl of the side chains can alkylate DNA. And shown in this red box labeled with toxic metabolites, you can see that what happens next once you have this phosphoramide mustard is that really the nitrogen loses one of the alkyl chains loses the chloro, and that ethyl group cyclizes back around onto nitrogen and giving this highly reactive, positively charged aziridine, 3-membered ring with nitrogen, right? This positive nitrogen is what attacks and alkylates is what is attacked by the nucleophile of the nuclear bases. All right, so this is what reacts with, for example, N7 of guanine. Because N7 of guanine is negative, it has that lone pair of electrons, and now this 3-membered ring is very strained, and there's a positive charge. Nitrogen has 4 bonds in this compound, phosphoramustid. All right, so just to note that acrolein is an annoying side product. that causes some toxicity and is thought to be, in some cases, really problematic and causes some dose-limiting toxicities for people. And specifically with this compound, that dose-limiting toxicity is the reason is really manifests as hemorrhagic cystitis, and is the reason that you need to give another medication. It's mostly because of this acrolein side product as well. So patients that are given cyclophosphamide, ifosfamide, and all these alkylating drugs like this, they often develop hemorrhagic cystitis, and acrolein production is the probable cause. It develops with the chronic administration of these drugs. As we saw, it's just kind of a side product, and it's a dose limiting, so it would be a cause for stopping treatment. If you remember, on Friday's lecture, I gave the example of a 69-year-old male with mantle cell lymphoma, and if you remember, before and after ifosfamide, so he was given ice, and the I in ice was ifosfamide, and before and after he was given Mesna. So this is the drug for hemorrhagic cystitis, and to kind of help this side effect, you can minimize the effects by doing that high water intake in the morning. There's bladder irrigation with thiol compounds, systemic treatment with compounds that quench those toxic products, so N-acetylcysteine and Mesna. All right, and so Mesna is then our first cytoprotective agent that we're going to talk about. It's really 2-mercaptoethane sulfonate, right? So the mercapto is this thiol group, SH on the end. There's CH2, CH2, and then the sulfonate is sulfur with 3 oxygens. And this is given, as we saw, prophylactically and also therapeutically for cystitis associated with ifosfamide, cyclophosphamide, and really these drugs with the 2 alkylating arms, chloroethyl arms, can cause this side effect. So it's injectable as an inert disulfide. And so what does that mean? Well, the inert disulfide would be here at the thiol end. Basically, Mesna, when it's delivered, it's actually 2 of these molecules end to end, right? So that there's a sulfur linked to another sulfur, and then another one of these molecules, CH2 sulfate, going the other way. So that's the inert disulfide, and that's what's injected in the renal tubules. It's converted to Mesna. So that disulfide bond would be cleaved, and the sulfur gets a hydrogen instead. And this is the active compound. So that disulfide has to be activated in the renal tubules to the compound that you see here. And then this compound, this thiol compound, it binds to and detoxifies those urotoxic metabolites like acrolein of cyclophosphamide and ifosfamide. All right, so why is that? The thiol, the SH, is very reactive. Sulfur is a very large atom. It has low pairs of electrons, so a diffuse electron cloud, and it's very nucleophilic. Then it's going to neutralize, react at the double bonds of the acrolein in a Michael addition and neutralize it. All right. So does everybody understand that the inert disulfide is just putting another molecule back end to end here so that there's a bridge between the 2 sulfurs of the 2 molecules? All right. And so this generalized mechanism is not something that you would be asked to draw out, that you would be asked to describe. I just, again, felt that when I didn't include it, people really want to know. And so what happens, what I would like is just that you recognize that if there were a drug with a nitrogen and CH2CH2Cl, you could predict that's probably an alkylating agent. That's a DNA alkylating agent. Actually, it can alkylate proteins as well. All right. But the mechanism of it is that there's a lone pair of electrons on this nitrogen, and they push density down the chains and enable the chloride to leave. So Cl minus essentially to leave. Chlorine is a very good leaving group, and so that's what it wants to do. It's also it's also got electron density, and so it doesn't like being near the nitrogen with electron density. It wants to take that electron density and leave. All right. So that's what's being shown there. And what happens when that happens is, so we've cleaved the bond to chlorine and then made a new bond from the lone pair of electrons on nitrogen to the carbon next to the chlorine. All right. So because that bond would be Cl minus C plus a little bit. So the C plus is attacked, or delta positive is attacked by the lone pair of electrons, giving you this highly reactive aziridine, positively charged nitrogen that can then be attacked by the nucleophiles of the nucleobases. There's a lone pair of nitrogen on N7 of guanine, for example. Remember that guanine is attached to the rest of the DNA strand. And once that's happened once, well, there's a second chain, so the same thing could happen. And this is how you get interstrand cross-linking, right? The molecule reacts with one guanine in one chain, and then it can go and react with another N7 of guanine on another chain and cross-link them together in this way. All right. So you can also get complete loss of the guanine itself. As we said, you can get DNA strand scission. This would be when the DNA strand breaks because the new bond is formed, and to balance the electrons, then the bond that's broken, for every bond formed, there should be a bond broken. The bond that's broken is to the rest of the DNA. All right, so that's cleaved, and now we've deleted guanine from the DNA over here. And then we can also get a continued reaction where once we've got reaction to DNA on one hand, the other alkyl chain could actually go and react with a protein. So often there are proteins docked on the DNA to perform certain functions. It's possible that the alkylating agent can cross-link those two together. All right, so really for your information and better understanding, but certainly wouldn't be tested in any form in a multiple choice exam. All right. And so now in the last part of this class, let's speak about then platinum coordinated compounds. So we've spoken about compounds that have carbon to add to the DNA. Now we're going to speak about compounds that have platinum to add to the DNA. So alkyl group really means carbon hydrogen, right? An alkyl group is carbon hydrogen. So we shouldn't call technically these are not alkylating agents, but we're calling them alkylating agents because effectively they do the same thing. They just do it through platinum instead of carbon. So that's the explanation. That's why it's part 2B, where part 2A was the nitrogen mustards. All right. So these may be drugs that you're very well familiar with. There's cisplatin. This was known as the penicillin of anti-cancer drugs, right? It's been as useful and ubiquitously used as penicillin has for bacterial infections. And then carboplatin, you can see that cisplatin has two free nitrogen amino groups on the same side, so they together, they're next to each other, and then two chloro groups that are next to each other. That's why it's cis. transplatin if this nitrogen was here and this chlorine was here, so that the chlorines are trans and the nitrogens are trans, that doesn't have any activity whatsoever. All right. So cisplatin it's important to have the cis substitutions there, and those can be changed to some extent. So in carboplatin, now we've got this oxalo group, kind of a bidentate dicarboxylic acid, in this case with a 4-membered ring attached. That whole group replaces the 2 chlorines, and that can be beneficial. We'll talk about that more. There's also oxaloplatin. In this one, there's the dicarboxylic acid or oxalate has been added on one side instead of the chlorines. On the other side, the nitrogens have been functionalized into a ring. And if you remember the principle of bioisosters in medicinal chemistry, here it's just changing these free amines to something that's joined by this 6-membered ring. So these are the 3 that are commonly used, especially in combinations. You might also have heard some stories of saproplatin. This was the first orally administered platinum drug. It was very useful for some men with prostate cancer. It was approved in Europe, just like picoplatin. They're not FDA approved here. And I think it was a little sad that these saproplatin seemed to just fail as being proven that it was better than the current standard of care. I think for many people, it showed very good efficacy and was as good as the current standard of care. And for them, it was the only option, but the FDA did not approve it. So maybe there's more to the story now, but this was one of the prostate cancer drugs that never got approved here in the US. And who knows, maybe it'll come back and be revisited. So really, there's just the 3 in the top row that we will talk about, but here it's just to show the concept of interacting with the DNA, that the platinum actually does bind kind of covalently with the DNA and disrupt the DNA helix. So here we've got the platinum shown in red. You could see it's making these interstrand or intrastrand links, and that causes the DNA to bend. So cross-linking really leads to DNA strand breaks or miscoding errors. Here you can see how bent over the helix is. And cisplatin also inhibits DNA polymerase. So if wherever there's a site of DNA replication, cisplatin can also disrupt that protein DNA interface. So down below are just some examples of how it could bind 1-2 intrastrand, so the same strand. On the same strand, it's binding to neighboring bases. All right, so just say N7 of guanine to N7 of guanine next to it, because there's a GG in the sequence. It could be a 1-3 strand. It can actually stretch a bit, so it skips the base in between, but it's straddling the ones on either side. And then you can also have the interstrand crosslinks, where it's bound to one strand on one side and it crosses over and crosslinks another base on the other side, because there's normally 2 interactions, so it forms 2 bonds with DNA. And what you could also see in this pretty crude figure is that it's the chlorine groups that have left in cisplatin, so the amino groups are still there. It's the chlorine groups that leave when cisplatin is equated. Really, it has to be solvated. It gets water added in place of chlorine first, and then those sites are taken up by the DNA when it alkylates the DNA, essentially. All right, so quite a crude slide, but still very effective at demonstrating the point. Just a little bit about, a little bit more to show, what else needs to be thought about. Really, if you have cisplatin coming into the cell, it seems like the metal transporters in the cell, transporters that uptake metals, or copper in particular, those copper transporters, those can take up the platinum drug. As I said, the platinum drug is hydrolyzed, then loses the chlorines one at a time, and they're replaced by water molecules, so they're equated. And then that platinum drug actually can be reacted with glutathione or metallothionein. These are some detoxifying mechanisms. So remember, glutathione is an important antioxidant in our cells that often helps get rid of toxins. When glutathione reacts with cisplatin, it then that resulting product can be pumped out and excreted by special GSX pumps. And then, so that would be kind of, if a cancer cell's upregulating that process, that would be bad, because then we've got less platinum drug alkylating the DNA. The platinum drug can also just be effluxed out by those same copper transporters. So as a metal, it's going to be targeted by metal transporters, but hopefully some gets into the nucleus where it will ultimately interact with the DNA and disrupt it in cancer cells. So cisplatin, as I said, it's known as the penicillin of cancer drugs. It was first FDA approved in 1978. And there's quite a long, interesting story about its discovery. Obviously, it wasn't necessarily being looked at for cancer directly. It was noted that it blocked the mitosis and cell division of some bacteria, and that they grew to enormous size. And so the scientists that observed that realized that then maybe that is blocking cell division and would be useful where cell division is the problem, as in cancer. So this drug is given intravenously, and still is, that's the formulation. The side effects that I would like you to remember really is, every time you think cisplatin, think cumulative renal toxicity. So it doesn't matter how long you've taken it, the renal toxicity is additive. It doesn't go away, right? So it's additive kidney damage, and this is really the dose limiting problem. The drug also causes myelosuppression, nausea and vomiting, some loss of hearing as well. It affects, so that's like a neurotoxic effect. But the main one to remember is cumulative renal toxicity, because that's so severe that it requires administration of a cytoprotective agent. All right, so we'll see what that is. Obviously, there's room for medicinal chemistry around these drugs, and oxaliplatin is the only one we're going to cover in any detail here, also known as L16. And compared to cisplatin, as we've kind of already alluded to, the NH2 is replaced by this cyclohexyl, so six-membered cycle, and it's still the diamine, all right, the kind of metadiamine. So this actually gives improved anti-tumor activity. If you remember this, the nitrogens don't leave. It's the other side of the molecule that leaves during equation. And so this may provide some structural stability, and it's actually improved the anti-tumor activity of oxaliplatin versus cisplatin. So as we see as well, the Cl- ligands, the chloride ligands, are replaced by this dicarboxylic acid called oxalic acid, right? So the ligand is the oxalato bidentate. Bidentate because one molecule is chelated to the platinum, is coordinated to the platinum twice. And this oxalic acid moiety improves the water solubility, so it just helps the platinum to be solubilized in the cell and reach a higher concentration then. So the main side effect of this drug is not cumulative renal toxicity. So this was one of the reasons also to try and modify the platinum drugs. Can we get rid of that renal toxicity? And the answer is very clearly yes. It was very successful to remove that cause of the renal toxicity. And the main side effect for oxaliplatin is instead neuropathy. This can be serious. It's really sensitivity to cold and numbness in the hands and feet, but generally it's a lot less serious than having this renal toxicity that could lead to the need for a kidney transplant, for example. All right. So this is a newer drug approved 2002 to 2004. And that's kind of this is the only drug we're going to use to demonstrate that principle of changing the coordinating ligands to improve the activity and reduce side effects. So as we said, cumulative renal toxicity is very serious and warrants a cytoprotective agent for cisplatin administration. That is amifostine or ethanol. And so hopefully you can see here a free nitrogen at the end of a chain, a flexible side chain. It's got an amino group in it, and it ends in a sulfur again, and the sulfur is phosphorylated. All right, so the sulfur has a phosphate group on it. And that's also important for its how it protects normal cells versus cancer cells. So it's used, as we said, with repeated doses of cisplatin to reduce the renal toxicity. It's also actually used to reduce dry mouth, xerostomia, right? Xerostomia is dry mouth. That's often caused by radiation treatment, especially in the head and neck area. When that affects the saliva glands, the parotid glands, the result is dry mouth, and this can actually help to protect those parotid glands. How does it work? Well, the free thiol, so again, the phosphate group is lost under certain conditions in certain cells, and there's an H on the sulfur, and that free thiol. So often with these compounds, it's the free thiol that you need for reactivity, right? So here again, the free thiol detoxifies reactive cisplatin metabolites in the kidney, so it protects the kidney. And why it's so effective is because higher pH, better vascularity, and higher alkaline phosphatase in normal cells. All right, so your normal cells are going to dephosphorylate amifostine to unmask that protective thiol. And so the normal cells tend to have alkaline phosphatase at a much higher concentration. They are at a higher pH. Remember, tumor cells tend to be low pH. So this reaction for alkaline phosphatase needs higher pH of normal cells, and normal cells generally have better vascularity, have better blood supply to bring this compound to them to protect them. All right, so this is very, again, focused on really helping the normal cells and not quenching the reaction in the cancer cells necessarily, because of their difference in pH. The side effects from this compound, so this is another example of every drug you take has its own side effects. So this is the cytoprotective agent to protect against the effect of cisplatin. but it also has problems that it causes, and those also need drugs to help prevent the effects or reduce the effects. So the side effects of amifostine are hypertension, severe nausea and vomiting, and it's really the severe nausea and vomiting that requires antiemetic administration. So again, I think thinking back to the kind of case study when somebody's being given a combination therapy, what would happen is the cancer pre-meds given on the days before would include these short and long duration acting antiemetics to just help the person deal with nausea. And it's not nausea from only the cancer drugs, it's also nausea caused by the cytoprotective agents. All right. All right, so really that's the end of these antimetabolites and alkylating agent examples. There's two sample questions, and maybe we can just spend a couple of minutes going with this. Which of the following statements are true for alkylating agents? They are cell cycle phase non-specific. That's correct, right? I see heads nodding. They react with DNA most commonly at N3 of guanine. No, N7 of guanine, or O6 if you're going to say oxygen, but N7, O6 are on that same phase, all right? Chlorambucil is more stable than mechlorethamine. Yes, yes, it is. It has that aromatic ring to delocalize the lone pair of electrons on nitrogen. So I think that's D. And we don't give these K-type style of questions anymore, so you wouldn't see this style of question on the exam, but it's still useful to just go through the options and check them. And so another one about antimetabolites, which are true. They inhibit the production of DNTPs. Do you know what DNTPs? Deoxy sugar nucleotides, right? They inhibit the production of DNTPs required for DNA synthesis. Yes, they do, because if they're acted on by those enzymes that make the NTP, the nucleotide, then they're going to block normal metabolites from being formed. They compete with regular metabolites for incorporation into DNA. Yes, they also compete because the DNA polymerases just keep adding 5-fluorouracil, NTP, and so on. Methotrexate inhibits thymidylate synthetase. No, methotrexate inhibits dihydrofolate reductase. All right, good. I saw people shaking their heads there. That's good. And gemcitabine and capecitabine are purine analogs. No, they are pyrimidine analogs. All right, so 1 and 2 only, I think. So just some examples of knowledge on that section. In general, we also try and have a few questions in the exam where we actually try and put it in context and somebody is being given drugs, but a lot of the exam will be on these fundamental principles of the mechanisms. All right. See you tomorrow.
Yeah,